Then we have to move on to Damiaan. I already introduced Damiaan at the beginning, but he is already here. So let me give the stage to you, Damiaan.
Yeah, thank you. So so I guess I'll jump right in because there's a lot to cover and we have about half an hour. Thanks for being here. To a little introduction about myself, Damiaan Zwietering. I work at IBM as a developer advocate. And I've been busy in data science basically for the past 25 to maybe even 30 years. So I studied computer engineering. I studied artificial intelligence in Utrecht when that just started. And since then, I've been spending my career, all my time working with data analytics and later on, obviously, data science and all the stuff that we can do today. So in discussing this talk, which is about AI and about analyzing COVID data, we also had the discussion that, nowadays, when you talk about AI and data science, everybody thinks about complex deep learning, big networks, that kind of analysis. While still there's a lot of stuff that we used to do, I would almost say, but we are luckily still doing, which we used to call data mining, and which is about structured data and just getting most of the data that is available. And especially in the COVID area, basically the data that was available in the beginning, that was mainly the data that was just the daily case data. So that is a very narrow data set, as I always call it. And I took it as a personal challenge, more or less, as a hobby project to start with about just over a year ago, to see what can I do with that very sparse data set. So that very long, narrow column of basically just infection dates. So I usually say I use 3 columns: a location, a date, and the number of infected people at that date. But if you reduce that, it's basically just a list of dates. It's just a list of dates that tells you when people got infected. So I really set myself the challenge to try to understand what is happening. What does an outbreak look like? How does that develop? And can we do anything? Can we do any projection about that? Can we get some intelligence out of that basically? So what I'm going to present today is everything. Is a lot that I developed last year myself. I started up with a full open source environment, just Jupyter notebooks, Python, and I just started analyzing the data. So everything that you see today is available, and I'll just start sharing my screen for that. There you go. So everything that you see is on my second screen, so I'll be looking sideways quite some time when I'm looking at the stuff that I'm presenting to you, and I'll try to keep an eye on the chat as well. But please interrupt me if there's any questions, but there's not that much time today to cover it all, I guess. So last year I set myself a challenge and said, okay, I want to make sense of what's going on in this disease outbreak, and basically setting myself the challenge of what can you do with time series like data. So everything that you see today would be applicable to other kinds of time series as well, I guess. So you might even think of water levels in climate change, or temperature levels, or anything that produces a time series. You could start analyzing in this way, and that's what I would want to show you today. What it comes down to is understanding what's going on there. So the subject of today is curve fitting. So the first challenge was, how does this develop, and what kind of curve can I fit to this kind of data to try to project as well? I mean, if you're in the rising part of the curve, you would like to know how it progresses, how it develops, and also how the disease spread would eventually go down again. So that is the curve fitting that we'll look at today. As I said, everything's available. I put it all out on my Git pages. So if you go to my GitLab pages, Zwietering, there's a project called Corona there. Wasn't that hard to come up with the name. And there's basically after a year of putting stuff out there, there's a pretty extensive README as well with all the documentation. So you should be able to find everything that I show you today and start working on it for yourself. I used a lot of different data sources. For example, you can see here I used Dutch data from RIVM. I used world data from Our World in Data. I switched for the US data as well. Thank you for the link. I switched to US data. First, I used the data from EU CDC, I had to switch to other data sources. There's examples of CDC as well. So there's quite some stuff that you can explore there. There's even a larger workshop that I can do. That is about half a day, I guess. So you can follow along. And in that workshop folder, if you click on there's lots of material that you can start following yourself. So there's some documentation. Maybe not. It's never enough, but it should get you started. And it's all about exploring curve fitting, modeling. There's lots of material there today. But today we'll concentrate on the curve fitting part here. Yeah, so I just started out with downloading data. So I found the data source, the first one that had reliable data worldwide was EU CDC. And I chose to first look at international data because I wanted to make sense of the way that a disease like COVID spreads. And if you're just looking at the Dutch data, you'll only get an impression of how it spreads under the Dutch circumstances. So that's always a thing that I start doing when I start looking at data. I say, okay, I need data from very different circumstances, because then if you find something that corresponds between the outbreak, let's say in Japan and Iceland and Brazil, and you find something similar, then it's probably a general truth. So if you want to find out the general underlying rules in a disease outbreak like this, you should look at data all over the world, because the differences in circumstances are huge, obviously. And if you then find something similar, it's probably a general truth. So yeah, so this notebook, which you can easily run for yourself. I mean, all these notebooks download their own data. At all the notebooks, there's just usually a wget statement on top. That simply downloads the current data set from the source that is used in that notebook. So if you run this in any bare bones notebook environment, if you just run on cells, it should download the data and start running. So it's a very easy way to get up to speed, I guess. So yeah, there's a lot of data manipulation going on, obviously, before you get to this graph. But basically, have a look, I would say. We'll concentrate on fitting the curves today. So yeah, the first graphs are these. So these are very well known. I'm using a data source here that only gave me data until half of December, the EU CDC. So we'll see other data sources as well. So it's this data set ends halfway December last year. But you can see the progress of the infections in the Netherlands in this case. Easily in this plot, and it's all interactive. So if you want to look at the UK, you can simply fill in the UK here and have a look at how it progresses there. So something similar already, but there's obviously lots of other countries as well. If you look at EC, which is Ecuador, for example, you see something totally different. I mean, they have a reporting problem, basically. That's what you see here. So they have this huge peak. They even reported negative cases here because they said, we reported lots of cases here, but by the way, there weren't COVID cases at all. So we're going to subtract that from the total. So you'll have to deal with all this kind of effects. So basically, this would be a very hard one for curve fitting. But let's concentrate on the first outbreak here in the Netherlands, which was more or less in similar circumstances during that period. We started doing a lockdown, obviously, after it started rising here. But this is basically the curve that we'll look at today. Because in the beginning, when I started this, everybody was talking about we need to flatten the curve. So my first question then as a data scientist is, yeah, we need to flatten something, but what exactly is it? So my first question was, what is that curve? So I had a look at the material available in science and in publications and previous outbreaks like Ebola and flu and stuff like that. So to see at least something to get an impression about the general way that something like this develops. So the first thing that you encounter is the Gaussian function, because at least for the left side, there should be a graph there. So at least for the left side, you see that something similar to what you see in a disease outbreak. So people said, okay, for the first way of fitting a curve to this data, you could use a Gaussian function, which is not a very complex function. It might look complex, but basically this is just a quadratic function. So this is a parabola, basically, based on the parameters of the function. And then it's an exponential power of that. So that already points you in the direction, more or less, how to fit curves. Because the first question I always say is, can you do something with linear regression as a first test on data to see what the main relations in the data are? So my first question is always, can I get something linear from here? So if you look at this expression here, you would say, okay, if I if I simply take the log, then I have a quadratic expression. So let's have a look how that what that looks like. So I simply started doing that. So here for the relevant part in the Dutch data, you have this logarithm of the data. And yeah, if you keep your eyes half closed from a bit of a distance and you take out the noise, this might be part of a parabola. So visually, at least, you would say, okay, let's see how well this would fit. So yeah, so based on this function here, I just took the logarithm and said, okay, then we should have a quadratic function left. So let's try to see if we can fit that. So if this is a quadratic function and you take the square root, you should have something that looks like a line, basically. So what I did is I didn't take the square root. I took the first derivative, which should then be a linear expression. So the first derivative of this one, just numerically by just doing the deltas between the points here, starts looking like, well, with a lot of noise, starts to look like a line. So yeah, as a data scientist and exploring all this data, I just said let's then try to fit a line to that. Which is pretty easy in Python with the right libraries. So this would be then the line that fits through that linear data. So now you have the expression here. So you have the intercept of that line, and you also have the slope of that line. You can calculate back to the curve and see how well that then would fit. So you just take the steps back. So first we reduced the whole graph to a line, and now we expand that line again to the graph to see how well that would fit. So that's what's going on here. It's just expanding the line here back to the quadratic expression, where you can see, well, it more or less fits this expression. More on that later, but there's a lot to say, obviously, and you can look at all the residuals and all the fit measures that you have here. But as a first exploration, you would say, okay, but this might work. So let's have a look. So then again, if you take the exponential of this one, you should have the original curve. So that's the next step. And then you see for the full curve here, you get something that more or less fits the raw data in this area. You can already start to see the problems cropping up, because in all the graphs that you see based on this kind of data, that it rises faster than it goes down. So you see that it already shifts a bit to the right to compensate for the tail of the distribution here, and then it doesn't fit very well on the rise anymore. So yeah, then again, looking at all the measures and looking at the actual way that a disease develops, also from papers and publication, you could say, okay, I might use a Gauss function for the rising part, but probably for the part going down, it's not really working at all. And they made some pretty big mistakes with that worldwide. For example, in the US, they said, okay, we can fit a Gauss curve to the rising part, so we'll just assume that it goes down in the same way, and we will have a total of about, what was it at the time? I think 60,000 infections, and then it will be gone. So yeah, if you just naively do this, you can make a huge mistake. So you should really look at the exceptions, and also if this works in all countries. So obviously I ran this for all countries. There's a notebook as well which just contains this whole code in a for loop over all the countries worldwide. You can have a look for yourself how that would work. So yeah, Gauss function, okay, it's a start, but it doesn't really work in practice, and it only works if you because there's an underlying probability here that is basically the reproduction factor of the disease. So if you start varying the reproduction factor over time, you say, okay, in the beginning, many people will get infected, so you will have a high R0 value. And basically after a while, the RT value, and after a while the RT will probably go down, and that accounts for the longer tail that you have. But then you have to make assumptions about this underlying RT and how you should vary that. And then it becomes more or less a self-fulfilling prophecy, where you say, okay, I want to use a Gauss function, and then I'm going to look at how I need to vary the RT function to get it to fit to the data. So then you're approaching it from the tail end. I was more looking for a general expression that would work in more circumstances. So looking at a little bit more of the research that was done the past years, I found, for example, somebody who applied a gamma distribution to an Ebola outbreak. Visually, you can already see that the gamma function which you can at least reason about why that would work in situations like that. You can see that it has a longer tail, so it might be more suitable for these kind of stuff. But it was very hard to tie the gamma parameters to something that was actually happening in the real world. So that is there's a couple of notebooks as well that deal with the gamma function, so you can have a look at how that works. And then I did some more research, and I found out that I did a lot of work in predictive maintenance in these past couple of years. And in predictive maintenance, you look at time to failure, which is the measure that you're looking at. So you have a machine running on the floor, and after a certain time, it fails or not. So that's basically what you do in predictive maintenance. And I was wondering at the time, can you use a similar approach when you look at the infections not as a daily probability of getting infected, but you look at the time to infection, basically. So you're looking at the same data, but you're just looking from a different perspective. So you're looking at the perspective where you say, okay, if I get people walking around in a society like in the Netherlands under certain circumstances, there will be probably a certain time to infection. So you're not looking at the daily probability anymore as a function, but you're looking at the time to infection as a function. In that area, there's a lot of experience, and I do have a lot of experience in that area with the distributions that are applied there. And one of them is the Gumbel distribution, which is a maximum value distribution. So, for example, you can use it if you look at daily temperatures. You're recording daily temperatures, and you then take for a certain period the maximum temperature in a country, for example, then those maximum temperatures will show a Gumbel distribution, and you can reason about the disease spread in a similar way, where you say, okay, I've got this underlying probability of getting infected, which I don't know, but what I see is the maximum time that somebody can spend not getting infected. Basically, that is the maximum that you have here. So the date that you actually see that somebody gets infected is the maximum function in this case, which is the actual infection. And we got those dates. That's basically the data that we have. So just under an assumption that the Gumbel function would work in this environment, I did quite some experience and started fitting that to data. There's a bit of a problem here where you say, okay, this is a probability function. So if you look at the cumulative function, obviously, the values are always between 0 and 1, so you have to do some scaling and you have to do some numerical approximation to see where exactly in the progress of this function are we in time, for example. So this is a bit more complicated, which is dealt with in this notebook. But basically, the approach is similar to what I did with the Gauss and the gamma functions. So I have this approximation function here, which basically tries to find out where exactly are we in this outbreak, in this case, again, for Netherlands data, where between 0 and 1 in this outbreak are we? And we're looking at the data, just at the rise of the data to see if it would fit on the downslope as well. So this is data until the beginning of June in the Netherlands, in this case. But yeah, feel free to start experimenting with all kinds of other approaches. So here I've done some numerical approximation to fit the curve that we see into the Gumbel function that you would expect between 0 and 1. And you can already, again, visually, you see that we're probably on the right track here. It's not something totally different. And then you can simply have a look at the Gumbel distribution function, which is, again, not that complex. It might look a bit complex, but if you look at the cumulative distribution function here, you see it's just a double exponent of a linear function. So again, how to reduce this to a linear function is just taking the log twice, and you should have a line, which you can then start fitting, basically. So that's it. It's the same kind of approach. So I take the double log, and I fit a line to that. And you can already, well, again, visually, and you can look at all the numbers and all the measures to see how well it fits, but at least visually you can see it fits pretty well to that area of the data. It doesn't fit to the whole graph, but at least to a part of the graph it fits pretty well. So then it's again, yeah, we have a line now, so we can just take the double exponent and see how that would fit to the actual data. So here's the cumulative distribution, and here you see the actual fit to the Dutch data, basically from March to July. And it's fitted only on the data until this point, more or less. So the rest of this is speculation, it's a projection ahead. So you see the raw data in blue, which is there's quite some noise in there. I used a weekly average window to take out some of the reporting effects here. So the orange one is the smoothed data for the Netherlands, and the green one is the fitted function. So you can already see that you can take it pretty well. Works in this way. Basically starting to confirm that a Gumbel function would work in this way. Then you can start, if you have the rise of the curve for a country, you can start saying things about when probably based on the current circumstances you would have the peak, when it would go down, how fast it would go down, when the last infection would be. Then obviously right away you run into the problem that there's not just one outbreak. For some countries like Italy or if you look at Switzerland in the beginning, they had pretty strict circumstances, and they kept it up for weeks on end. And you can see that under those circumstances, a Gumbel function works pretty well. But then obviously you can have more than one outbreak in a country, and you can have outbreaks under different circumstances as well. So what I was wondering, if you could reduce this whole curve, the orange one, let's say, the smooth data, not to just one line to fit one Gumbel curve, but to fit multiple lines and see if you could detect multiple outbreaks in that way. So that's the next step that I took. I found there's a very nice algorithm for that, multivariate adaptive regression splines, which is also available as a Python library. So that's easy to use. And what that basically does is exactly what I was looking for, is that it doesn't try to fit a line through the whole data that you offer, but it tries to fit a series of lines. So basically, it's a time series clustering algorithm. It tries to find clusters of points in a data set that together show a linear relationship. So in this case, based on the parameters, because you can obviously parameterize it, you could also parameterize it here that it finds 5 or 6 or 7 or 18 lines in this data. But basically, if you look at look at the measures and look at the parameters, in this case, under these parameters, it found basically 2 lines in this data set. So then my next question was, can I then fit 2 Gumbel curves and see if they, in combination, can show you what it looks like? So here, for example, you have again the Dutch data, and if you then apply this Earth function to that, you have a set of lines. So basically, here's a line, there's a line, there's a line. I filtered this out because this was in the beginning just a lot of noise. So I was just looking at the beginning of the outbreak for my first fit. And then it's basically the same as we saw before. Try to fit a Gumbel curve to each of these lines that you find, and you now have multiple lines. That should give you multiple curves to fit. So I'm going to skip a lot of material here because I obviously spent quite some weeks on getting this to work in an automated way. So I would invite you to have a look at it for yourself. The material is available. I basically ended up with these kind of fits. So here you have, with the current parameterization that I use for all the data for the Netherlands, in this case, from January to September for this year, this is my multiple fit on that data. Which is a very interesting approximation. Again, this is a clustering, so you could take a very rough measure and then only get a couple of curves. So I try to make a more or less try to find out what interesting parameterization would be to draw some conclusions about. And for now, you can see that if you look at the data for the Netherlands in this case, you get already 27 waves. So I'm never talking about the second or the third wave, which I already had in the beginning. And I then try to tie this to what actually happened, in this case in the Netherlands, but obviously for a lot of other countries as well. And so, for example, in the beginning, you see this lower green wave here, which is first fitted, which are basically the infections that came into the Netherlands from the outside. Then you have this large outbreak in Brabant, which is very well known during Carnival last year. And then you see that the larger cities start to follow, but not that fast. And then things are already going down. And again, here you see a lot of outbreaks that you can, for example, relate to people coming together for Mother's Day or for Easter. Here people are returning from holidays. Here the schools start again. So you can tie this very well and get quite some insights if you look at the data this way. And an additional bonus is that you can obviously project this into the future. So it's not easy, obviously, and probably impossible to detect future outbreaks, because I can't predict if people are going to a wedding next weekend and start infecting each other. But as soon as I see the first effect of that outbreak, I can model it and see where it would end up. So things are looking pretty well in the Netherlands now, because we do a lot of vaccinations now as well. So things are going down. But yeah, I see that there's already again a little outbreak here, which will probably last well into to July for now. Yeah, it's already half an hour already. A lot of material, but basically just looking at how can I reduce all this data to a line, fit a curve to it, then take a series of lines and find out if you expand that back to the corresponding curves, if you get something that you can recognize and where you can deal with. So obviously I had a lot of discussions about this way and this approach and how useful that would be to use in practice. Right. Any questions for now?
Yeah, first of all, Damiaan, thank you very much. It was very nice to see all the visuals to like actually see the data. So that was quite nice. Yeah, so Esmaen has already posted a message, but on the right side of your screen, there's this Q&A box. And if you fill in your question there, we will see it and I will ask them to Damiaan, and then you will get an answer.
Yeah. Again, I'll just click through to the place where you can start exploring for yourself. So in the README, there's also pointers to a couple of related stuff that I did. For example, I made an alert radar where the source code is here, and in the README of that repository, you can click through to the world alert radar that I made. Now I'm very bad at front ends, but I just cobbled together some stuff with Folium and mapping and some calculations. So, for example, here, if you want to know about your country, there's no built-in search function. So you just look for the Netherlands, for example. You can see the current reproduction rates of the Netherlands for today and yesterday. You can see that we raised 6 places related to yesterday, so we're a little bit on the rise. You can see here, and if you click on the country, you get this fit. So if you want to explore a little bit and see how this fit works for countries over the world, you can have a look at this radar. And what it shows on the map here is basically if cases are on the rise or not. So everything that's red here has a reproduction factor over 1. So you can see where stuff is still going wrong or right worldwide. So you can see that we are not yet out of the woods in Europe, for example. I mean, there's cases in the United Kingdom, for example. They are pretty fast on the rise again. The numbers are very low, but there's something going on there. So that's basically what you can see in this mapping.
Yeah. So this is very. I don't see any questions coming up, but I see some comments. So one person, Geronimo, is thanking you for sharing this, and I also want to thank you because it's very interesting to see all this, especially this map. I think it's really interesting to see that we're doing better than some countries, but we're still not in the best optimal zone yet.
No, exactly, and it's very fragile, to be honest. So if you look at the difference between, there's always a discussion going on between the flu and COVID. If you look just at spread, you can see that the flu basically is a little bit everywhere, but COVID is very local. So you can do very well as a country, but if there's one town where people don't behave, it can easily spread out again from there. That's what we've seen a lot of times this past year. So it's very unstable situation still.
Yeah. Okay. So in the meantime, there's actually a question that has come up.
Right.
So it's Damiaan. Thank you for the presentation. I'm an anthropologist, so I visualize the pandemic alternatively and more socially as opposed to numbers and lines. How might my scientists create a symbiotic relationship with their varied data presentations?
Yeah, that's a very interesting question, and I spent quite some time last year in discussing how this kind of graphs would be useful. For example, so if you let's just take one, which is Switzerland in this case. So if you have this graph based on numbers, how can you relate that to actual behavior in a country? So I talked to some people. I don't know if there was an anthropologist, but at least a social behaviorist as well, where I said, okay, if you put this together to a calendar of events, for example, in the country. So you say, okay, what happened here is people coming into the country on holiday, for example. That is, you can tie the starting point of that outbreak to actual behavior in the country. You can start getting an understanding of what kind of behavior causes outbreaks or not. So the first step would probably be just take a calendar and have a look if you can tie this outbreak to something that happened in the country. But then it's also very interesting, and I talked to the Red Cross about that, which are very looking at behavior, where I said it could also be a behavior that's not localized, but it's more tied to a certain group of people. So that could be Easter, for example, for Christian people, or it could be something related to the Muslim religion, where people are very much looking at locations. So, for example, for the stuff related to the Muslim religion in the Netherlands, they look at Rotterdam. But then I found a similar effect in some place in Limburg in the Netherlands. And he told me, yeah, there's also a large community living there. So if you stop looking at just locations, but you look at kind of people and the kind of behavior that they expose, you could probably find that back here as a outbreak individually, and you could start trying to understand what's going on there. How do these people behave, and how does that affect the outbreak of the disease? So I think that is a way to start tying this all together.
Yeah. Okay. Yeah. I also think it's complicated, but it would be very interesting to see all those things together. So like we're a bit running out of time, but there's one
Yeah.
question. There's
Yeah.
one question still that I would like to go into. So it's from Jelle Donners, and it seems like quite a big assumption to attribute individual waves with a certain cause. Isn't it also possible that the waves simply have a more complicated pattern than the simple curve shapes?
Yes, obviously, but that ties a little bit into the remark that I made at the beginning. This is a kind of clustering, and clustering is always is not there's no one solution to a clustering. So basically, the one endpoint is you take all the cases together and you say they all behave the same, and the other end of the spectrum is you say each case is an individual behavior. So what I try to do here is find a compromise between those 2 points, like putting everybody into one bag or looking at everybody individually. So I looked at an interesting, and that is not a scientific thing. I looked at an interesting clustering which you could use to find out about how people are behaving. And basically the answer to that is any other clustering that fits well enough for your for how well you want to fit those curves. And any other clustering would be fine as well. So the main thing that I found out is that if you use the Gumbel curve in this case, the Gumbel distribution, you will find a reasonable amount of curves where you can start understanding what's going on. That's the answer. It's a very practical approach.
Yeah, thanks everyone for asking the question. Thank you for Damiaan for sharing your code. I see a lot of people thanking you for that. I think they find it very interesting that they can also take a look at it afterwards themselves.